back trying to write Wasm binaries with PureScript. I claimed before that we were in figuring things out land, but to be honest, we're in fumbling around land here. But that's all good. Let me put the microphone over here so you can actually hear me. Okay, so let's get back into it. And I know I opened a PureScript file here, but really I think we're just going to keep going in JavaScript for a while until we have an idea of how any of this works, really. Okay, so my idea was that I was going to say, let's create a buffer here. And that's going to be, I think what we need to do is we need to say buffer buffer maybe. That's probably not right. That is probably not right. Buffer? Or is that just a global? There's a buffer module. Okay, so the buffer object is available as a global. There are additional buffer related APIs. Slow buffers, none of that matters to me. Buffer, okay, whatever. Buffers and character encoding. So we do not want any encoding here. So how do I tell it to how do I just tell it to use raw bytes? Okay, so let's just create a new one, I guess. We'll see how that works. So they usually use from here. But I don't want to do that. I just want to allocate one. Okay, so alloc is the class, is the function we're looking for, I think. So let's do alloc. So alloc. And we're gonna pick a size. So let's just say 124, which is way larger than whatever we're gonna need here. So this gives us back a buffer. Okay. And so now, let us figure out how to write to a buffer. Okay, so buff dot. Okay, here we go. Dot compare, dot copy, entries equals fill, includes. Okay, so there, now we're getting to the fun stuff. That's reading from a buffer, but we're going to be writing to one. So let's just skip the read stuff. Okay, value. Right, there we go. So this writes a string. I do not want to write a string though. I think. Okay, here we go. So this writes big ints. Is there just a right number? Right flow, right int 8. Here we go. 16 big endian 16. Is that LE lower little endian? There we go. Okay, so yeah, these are the things we care about, I think. So I'm just gonna try to write. Well, if we want to just write bytes, we're gonna use int 8s, right? Okay, so because a single byte is an int 8. So let's try that. So let's say buff.write int 8. Okay. Oh, it requires me to write at an offset. I was hoping that we could. I was hoping that we could just use this as a just write bytes as if this was a buffer that we were filling up, but apparently it's more like an array that we're writing into, I think. So can I use a buffer as a I was hoping this could keep track of the offset at which we had written before, but that's probably not the case. Okay, that's fine. We're just gonna write ints then. Int 8s, which is already a weird one because this is a signed 8-bit integer, but how do I write an unsigned 8-bit integer? Is there a writer like a write? Ah, here we go. These are the ones, uints. So unsigned. Okay, so that's the one I care about. So we're gonna write a uint. And how about we write the string Wasm essentially? So let's find the ASCII table for things, I guess. So this looks like an ASCII table. So if we want to write the W, does it let me? No, it doesn't. Okay, so W is 7.7. Okay. Let's write another one. Or does it just let me write more than one? No, it doesn't. Okay, so we have to pass it an offset, right? So the first one goes at 0. Second goes at 1. So small a is 6.1, according to this at least. Maybe it's the other way around, actually. No, it's this way around. Okay, so WA, what's the S? S is down here, so that's 7.3. And we're gonna write that at offset 2. And let's just put semicolons in there. And then the last one, which is gonna be the M, that is going to be 6D. So, well, I guess. Oh, this is hexadecimal. All of these are. Okay, so then we're just going to do that. So 6D. And we need to make all of these into hexadecimal numbers. Okay, that makes more sense, I think. Maybe. We'll figure it out. Okay. So. And then afterwards, let's just console.log the buffer for now, and then we'll interpret it as text and see if that gives us the string Wasm back. Okay, so let's say experts.mess bytes byte t byte. Just gonna do nonsense here. That's just going to be a function that we call from PureScript to mess around with things. And eventually we're going to wrap this up into a nice little API that we can hopefully use from PureScript. That's the goal anyway. All right, let's see what's happening. Exactly. That's the one we've not used so far. So let's go into our main file here and say that we want to import byte byte, and let's just in effect unit, and we'll do byte byte here. We'll do that one more time. Build succeeded. I wanted to run this actually. Thank you very much. Buffer.alloc is not a function. So here we go. Things get interesting. I thought that was exactly, oh, right. That's not, I thought we figured out that buffer is actually global, so I can't import that. Okay, so that's a very large buffer, but only the first 4 elements are written. Okay, so what we're going to do now is we're going to try and interpret this as a string, I guess. Or we could say, let's just allocate a buffer with just enough space. And then how do we turn this into a string? So is there a decode here? Buff to string, here we go. So this is, so buff, and then we do buff to string, and then the encoding here is going to be UTF-8. Because the first, because we wrote this in ASCII, but just so happens that ASCII and UTF-8 align, and so that's Wasm. So that works. Okay, cool. So we can write bytes into this thing, and we've got to keep track of the offset somehow if we wanted to make this into an API. And we'd need to somehow make sure we truncate it at the right point when we actually want to turn it into something, because otherwise we end up with a bunch of trailing zeros. And maybe we'll wrap this up in some node stream, or maybe there's a module that does that. But I think that actually should be good enough to get started for now. Okay, so now that we know how to write some things into a buffer, let's try to figure out what we need to write into a file for this to become a Wasm binary. Now, let's actually start by trying to write the buffer into a file in the first place. So I'm assuming that's file system stuff again. Is there a write buffer? Is there a write file? I'm assuming there must be a write file. So write file takes the file path and data, and this is possibly a buffer. And the encoding, the default is UTF-8. We're gonna tell it to say null here, so that it writes raw bytes. Okay, so let's do that real quick. So let's in here say fs.writeFile, and we're gonna say the file name here is hello is byte.wasm, and the data is gonna be our buffer. And we said the options were either an object or a string. The encoding option is ignored if data is a buffer. Okay, so we don't care. That's good to know. So it doesn't try to re-encode anything. That's good to know. Okay, and so this takes a callback actually. So this says, well, in case we get an error, let's just print that out. So console.error. So something went wrong when writing the buffer, and we're gonna say, well, the error went wrong. Okay, and all right, so let's see if that works. So I'm running npm. Something went wrong when writing the buffer null. Okay, yeah, that's so only if we actually ended up with an error. Shall we do this? Let's actually use curlies, because otherwise it's way too easy to mess up. Let's do this again. Okay, so now does this write file, does this clear the file before, or does it just append? I think that's probably done a different call, right? So yeah, I'm just hoping that that worked. So let's see, that would be more, the file is, what do we call it? Bytes.wasm. Okay, and so if we interpret it with more, which interprets it as text, it says wasm, and it especially says wasm just one time, because that's important, because while we wrote it twice now, it did not append. So this is just what it says. So that's good. Okay, so now we know how to write a buffer to a file. We know how to write individual bytes to a file. So now let's try to figure out if we can write the binary format of WebAssembly. And this is a specification. And the specification is pretty good, but I haven't tried reading the specification for the binary format so far, and I've never actually written binary formats, so this is all new to me. Okay, so the binary format for WebAssembly modules is a dense linear encoding of the abstract syntax. As only terminal symbols of bytes. A byte sequence is a well-formed encoding of a module if and only if it's generated by the grammar. Okay, yeah, that's fine. I do not care. So here we go. It looks like, yeah, it actually talks in individual bytes. So the uint 8 is the thing we'll be writing a bunch. This all looks like pretty standard grammar stuff. Okay, and I think this one we'll have to keep in mind. So vectors are encoded with a U32 length. So this is not a single byte, right? Because U32, well, you can only fit a U8 in a single byte. So this is more tricky. So maybe we should just make ourselves a function right here, which says write vector. And I don't know if we need that yet, but or maybe we can just keep that in mind. So I'm just going to make this a comment, but I'm going to say when writing vectors refer to, and then hope, can we link this? Yep, so I'm just going to put that in there. So we can come back to this when we're ready. Like so. Okay, well, let's see what okay, so the binary format defines a bunch of stuff here. And then let's see if we can get back to the overview here. And so I think the top level stuff is actually a module, right? Because we don't want to encode individual, well, we're going to eventually encode individual values, but what I really want is I want a single module for now. I want the simplest possible module. And so the binary encoding of modules is organized into sections. Most sections correspond to one component of a module record, except that function definitions are split into two sections, separating their type declarations in the function section from their bodies in the code section. Okay, so a WebAssembly module consists of a bunch of stuff. And apparently these the binary encoding matches this mostly, but it separates the type definitions for functions from the code section, which is a good thing because that means that you can read the exported interface of a module in one place without having to also skip over a bunch of code actually. So each section consists of a 1-byte section ID, the U32 size of the contents in bytes, and the actual contents. Okay, so that's good to know. So that's what a section looks like. We're going to start out with a byte, which is just going to be the section number, and the section numbers are explained down here. Okay, and we do need to make sure we write the correct size. So let's write a function here, which we're just going to say write module. Okay, and this is going to return a buffer eventually. And we don't know how many bytes we need for now. I'm just going to say, I'm just going to make this large. And then we'll write however much we need and truncate afterwards or something. We're going to keep count of the offset here. We're going to start at offset 0. And we might we're going to keep count so that we don't overwrite ourselves, and we can use this to figure out the size at the end. And yeah, we're gonna see how far we can get. So custom sections. So what I really want to figure out is what's the most, which sections are actually needed. So I'm wondering if we can, so this is a, okay, so now we go, here we go. So this is, I think, what we actually care about. So the encoding of a module starts with a preamble containing a 4-byte magic number, the string Wasm, and a version field. The current version of the WebAssembly binary format is 1. Okay, so these are the things we're going to need to write first. So that's the header that every Wasm module begins with. Okay, so let's do that. So buff dot, and I'm just going to paste this in here. And then we're going to do a bit of editor stuff, I believe, to, oh damn it, we need to make sure we keep that in the right order. So these are the 4 magic bytes, and this is the version number. Okay, so so we're gonna say buff.write uint 8, like so, and we're going to write this as at offset, and then we're going to increase the offset by 1. And more nonsense, all the nice low level idiot stuff. Okay. And then we're just going to write this one. Like so. And because all the others are already initialized to 0, I'm just going to increase, I'm just going to write this at offset. And then I'm going to say offset plus equal to 4. Right, so we're going to bump this by 4 bytes after having written this thing. And so this is the special string \0, which again, we don't really need to write this, but I figured let's just write it at least once. And this is supposed to be Wasm. And if we remember, or look down here, that's exactly what that is, right? 61736D. That's exactly what that is. So that matches what we had done before. So that's good to know. So this is what the thing starts with. So a module then is magic, which is this thing, version, which is this thing, and then all of these. So let's see, which of these is actually required? Do we need any of this? What happens if I were to just write this to a buffer and be done with it? All sections can be empty. Okay, so this should be a valid module. Okay, so how much do we write here? We write 4 and 4, so 8 should be good enough, right? So this is a module, and then we're going to return the buffer at the end, right? And so I'm just going to say here, I'm just going to say write module, which is actually a terrible name. So this is the module buffer. And then we're going to, I'm just going to call this buff so that the rest of the code matches up. Okay, so hopefully that should actually give us a, okay, so hopefully we created a buffer. That looks about right. So let's go and say in main.pers, we're now going to try to run byte.wasm. And well, let's see where it failed really, because that looks about right. That looks fantastic. Inst exports.add10 is not a function. That means the instantiating worked, right? So did that actually, wait, did that actually create a, did that actually work? So let me see what happens if I do wasm time on, what did we call it again? We called it byte.wasm. Okay, so wasm time does not explode on it, which I think is a good thing. Let's try to write something that is nonsense. So rather than a D, I'm going to write an F here. We're going to run spargo run, and then byte wasm, and that fails. Okay, fantastic. So we are writing a valid Wasm module. So this is the version. So the version is 1.0.0.0, like so. So that's great. So we are writing the minimal Wasm header here, and now we can look into the different sections that we need. We can skip the ones we don't need, and we can insert the ones we care about. So I'm going to say, let's try to start moving into PureScript. It might be too early to do so, but well, where's the fun in playing it safe? So buffer.pers. So what do we care about? We want to be able to write a uint8 into a buffer, and the signature of that is going to be a buffer. It takes a buffer, it takes an offset, and it writes a byte. So I don't know if we have a type for that in PureScript. I'm just going to make it an int, but maybe we should try to figure out if we can if we have a type that only only matches 8-byte, well, a byte. So buffer is a foreign type, so foreign import data buffer, and it is of type, well, I mean, I guess we can call it a type for now. That works. So it does not have a constructor. And the way you create one of these is you write alloc, and it writes this stuff into the buffer and gives you infect unit back. You need to import effect here, of course. And so now let's do alloc, which should give us a buffer, and we're going to alloc with a certain size. So what else did we do so far? Main.js. We wrote a bunch of bytes, and did we do anything else with the buffer? We toStringed it. Let's do one that is a little more helpful for us, one that turns the buffer into a string. And if I remember, there was a toString here where we could say hex for the encoding. Is that right? I think so. Hex prints this thing. I was hoping that maybe we could get a bit of a nicer representation. Okay, let's just go with that for now. And then we'll create the buffer.js file, which contains all the definitions that we declare here. So we need to do this. So this is alloc. It takes the size, and I don't think we need this to run in brackets here. And then gives us back a function that calls buffer.alloc of size. Not particularly exciting. We need write uint8, which takes a buffer and an offset and the byte, and then it writes a uint8 into a buffer at offset. Sorry, that's buff.write uint8 at offset, and we write the byte, but I think the offset goes last, so we write the byte at offset. That's what we do. And this highlights strangely, so I'm just going to say bit here because I do not know if that means that that's a keyword. And then the last one we need is toString, which takes the buffer and just returns the string. And so here we do buff toString. I'm going to say hex and hope that that works. Okay, so let's try to compile that. Okay, so now file compiles now. Let's try to start moving some of our definitions into PureScript land. So we said that we wanted to make a Wasm module, which was a function that creates an effect of buffer. So when we make the minimal Wasm module, we're going to alloc a 8 bytes, which is going to give us back a buffer. Oh my. Guilt Christian is now following. Hello, how's it going? Welcome to some low-level nonsense that we're doing here. Right now we're moving some of the JavaScript we just wrote, some of the low-level JavaScript we just wrote to create a Wasm module into ooh, you've got an octopus, that's pretty sweet. Into PureScript. Might be a little early to do that, but well, we'll figure it out when the time comes. So now we should be able to say buff. So what do we need to do? We need to write a uint8 of into buff, and then the offset here is going to be 0 for now, and we are going to write the value of 0. So let's just make sure that PureScript parses hex literals the way I expect. It does. And so what we need to do at the end is return a buffer. Okay, all that works. So this whole deal where we we need to keep the offset around. I'm gonna keep that for now, but eventually we'll if this pattern doesn't change, we're gonna skip that. We're gonna switch this up and make the whole thing either a writer or wrap some other mode around it that keeps track of what offset we're at. So we're gonna do that, and then the last thing we need to do is write 1 at the offset 4. Okay, and so this should just give us back a buffer with the same contents as we had before. And then the last thing we're going to do is we're going to say write buffer to file, or actually I'm going to say write to file because I want this module to be imported qualified, and that takes a buffer and it gives us back a callback, really, or you're supposed to specify a callback, and then the whole thing gives you back a unit. So what's your callback? Well, the callback really has to deal with an error, which may or may not be there. So really this is a maybe error, but this is a Node API, so it's probably actually going to be a nullable, which I do not have yet, but that's fine. So this is a nullable error. And error is also, we call it exception? I think it's error. We'll figure it out in a bit. And well, you can do whatever you want. And a callback. So nullable is not known. That's fine. Let's add that to the project real quick. So that's nullable. And we'll also need the error type for we don't use this one because the API is terrible. What's the exception type again? Let's figure this one out real quick. So error is what it's called, I believe, which is the type of JavaScript errors. There we go. It's called exceptions. Okay. And so if we go back in here and say Spargo build, well, it did copy a bunch of stuff, but it's saying that we have import this stuff, which is correct. Just need to, oh, actually, there we go. Now we can import this stuff. So what's the problem here? It's saying we didn't implement write to file, which is true. So let's do that real quick. So inside source buffer.js, I have claimed that I'm going to write a function write to file. Now signature-wise, this takes a buffer and then it takes a callback, and then it's going to give us an effect. So we're going to need to wrap things up a little bit. And so what did we do again? I think what we did is we required fs, because yeah, that's certainly going to be necessary. And we might break this out into its own little thing if we want to eventually have this also run in the browser, because then we can't just require fs like that. So we're going to write a file, and the file path is probably the thing we need to accept as the first argument here. So let's do that. And then we're going to write a file to the path, and the file that we're going to write is the buffer, and then we're going to call the callback. And because I made this somewhat idiomatic PureScript API, which I maybe should have done. You know what? We're going to do it properly, because maybe it's going to help people figure things out. So what I'm actually going to do is I'm going to add one more import, and you might be able to use this in your own stuff, and I think it's called functions, but let's just double check real quick. So what we're going to do is we're going to type this thing as if it was an actual, we're going to type it exactly like you'd write the JavaScript. So what do we want to do in the JavaScript world? Well, we want to accept all these arguments like so, and then we just want to pass them in here like so. Okay, or if we wanted to be even crazier, we'd accept them with a comma separated list. You know what? I'm not going to do that. That's way too annoying. We're just going to do this. But the important bit is that these things are a little weird. And we're going to wrap this up into a nice to use PureScript API. So I am going to all of these things happen to live in PureScript effect, which I'm already depending on, so I don't need to add anything here. I'm going to now call this thing impl, and then back in our PureScript file, we're going to call this thing impl. I'm going to change its type up a little bit more, because what you're actually supposed to provide here is an effect fn1. Rolls right off the tongue, and it's going to take two arguments. It's going to take, or like, the nullable error and unit, which is the type it's returning. Okay, and so this is a type that represents a JavaScript function. Of the shape that you're supposed to pass in into here. And because we're still using the effect on the outside in the PureScript signature, let me show you that real quick. Because we're still using the effect over here, we're going to need to still leave the the thunking essentially in place. So so let's write the file. It's going to have the more PureScript syntax. So this is going to take a string and a buffer, and then it's going to take the callback. But this time around, the callback is not going to be an effective hidden one, but it's going to be a regular PureScript function. And we're also going to return a maybe error rather than the nullable, which is the note equivalent of a maybe. But in certain ways, it's unfortunately broken. So in PureScript, we should not use nullables apart from the FFI layer. Okay, so this is the signature I want to go with. I'm going to take, this is the path, this is the buffer, and this is the callback. And now I really just want to call write file impl. Where will the Wasm be generated? Are you generating it? Exactly, yes. I am. We are making, that's exactly what we're doing here. We're creating a buffer, which is a node way of saying an array of bytes. And we're writing those bytes to a file. And because, well, the bytes are really the binary format for WebAssembly. That's the hope anyway. Right now we're just writing the WebAssembly module that doesn't do anything. But eventually we'll write one with hash, with actual functionality, right? So we're going to pass the path and the buffer through. And now we're going to need to do things with the callback. So what does the callback really do? So we're going to make an effect fn1 here. And if you look at the type of this, this accepts a function from a to the effect of a. Is that right? No, of r, which is a unit in our case. So what does this actually take? This gets the nullable, the nullable error here. Okay, so maybe there's an error here. We're just going to call that thing our error for now. And okay, and then what we actually want to do is we want to call our callback, right? But if we try to just pass it the error, it's going to choke on it. Well, let's import maybe first. Exactly, yeah, it's all, this is, I'm just messing around here really. And so this complains that it can't match the type maybe with nullable because, again, the Note API does not actually give us a maybe. So what we're going to do is we're going to say nullable to maybe, I believe. And maybe that's wrong, but we'll figure it out. And let's see if we can import that. Is there a to maybe? And apparently there is, as you can see up here. So now it has imported this and the whole file type checks. Okay, so let's see what is the API we've actually got here. So we've got okay, maybe format this a little nicer. Okay, so what we've got the buffer type. Okay, so this wants me to format just things like this. We've got the allocate function, we've got the write uint function, and we've got the toString function. And the last thing we have is the write to file. And we're not going to export the impl one because that's internal to our stuff. And it complains because we're not also exporting the offset type, which is just an int, but it's a little nicer to read with the type synonym. Okay, so that's cool. And then we're also going to export the make Wasm function, and that's just really, that should be written in, maybe we're just going to move that out of here into the main file because that's really where it belongs. So let's just do that. So we're going to say make Wasm module. We no longer need this function because we can do this inside PureScript now. And now it's going to start complaining because these things don't work. But we'll do this. Okay, so make Wasm module returns an effect buffer right now. We're going to change that up, but we're definitely going to need the buffer type anyway. So let's just import that. And I'd like these to all be prefixed like so. Here we go. And this ends up returning the buffer here, but I really don't want to return it. What I want to do instead is just write it to a file. So let us do that. So we're going to use buffer.write to file, and it's going to take a file path, and we're going to say, well, byte Wasm, why not? Let's try to execute the one we're passing in here, or let's try to run the file that we're creating. Let's say Wasm module, opening bytes, or entire executable. So, well, at some point it's going to be an executable, really. Well, not executable in the sense of an x86 executable, but in the sense that, yeah, we can run it with Wasm time, which is a Wasm engine. It's a Wasm module in the sense that it exists on the file system. It's just a byte representation of a binary. So yeah, it's a binary format for specifying code. And that's what we're writing, but what the JavaScript on the other side is doing. So I'm using Node here, which has V8's Wasm engine built in, right? So what I can do here is I can read a file, compile the Wasm, right? Compile the bytes in that file into a WebAssembly module, instantiate it, and then run functions from within it. Well, we created one of these things before, which had a function add 10 on it, but we're not at the point yet where we can actually create a module with functions in PureScript. But once we get that, this code is going to run again. But really, we can. The thing that's cool is that we can get all the way down here, so we can get to the point where it instantiates the module, which means that we have written a sequence of bytes that represents a valid WebAssembly module, right? And so that's basically what we're testing here. So really, what I'm going to do is I'm going to log successfully created a Wasm module and made sure the capitalization is right here. Okay, so and I need to stop writing non-functional languages. So write to file takes a string, which is the file path, a buffer, which is buff. What does it take? And the last thing is its callback. So it takes a callback, which takes maybe error. And it's saying, well, I don't have a callback, which is right. So maybe error to effect unit as an argument here, which is going to be the callback. Here we go. And we need to import maybe. Let's just do that real quick. And we need to import error. All right. So now when we wake them out, after making a Wasm module, we get an error. Well, maybe we get one. So let's just do case underscore of. So in the nothing case, things worked out. We don't get an error. We can try to run this Wasm. And in the just case, we're just going to say console.log failed to instantiate failed to write the Wasm module. Wrapping a node library which compiles a Wasm buffer and executes it also, I think. What we're not wrapping a node library, no. Really, because Node wraps V8 really, right? So Chrome's JavaScript engine, it has a Wasm interpreter or a Wasm engine inside as well, because, well, V8 has a Wasm engine. And so we're accessing that. So there's no Node library here really. That's just that it comes with Node because Node wraps up V8, right? Okay, and so the hope is that when we do a Spago run on this, we should get to the point where we successfully created a Wasm module. And this explodes because add 10 is not a function, which is true now, and we can just console.log exports. And so now we should get an empty object. So yeah, we instantiate a module. It doesn't have anything in it, so that's just an empty object here. Oh, totally didn't think that. That's amazing, right? WebAssembly is super cool. And the best part is going to be available basically everywhere. I'm going to be able to mess around with it. So there's an export here that we're no longer using. That's correct. That was just for us experimenting. So we don't need that one. And we are going to need that one, but we're going to put that somewhere else, maybe in here, because hopefully we won't be looking at the FFI for this main file all too much anymore. It's amazing that Wasm was really nice. It's been developed in so long. Well, it's designed, or like, well, it was initially designed by a few people, but now it's designed by committee, right? Which means that it's moves rather slowly, but at the same time, the things that it actually ends up getting are implemented by all the involved parties. So you actually get a real cross-platform binary format, which is amazing, because we don't really have that. The JVM was maybe the closest, but the JVM is not really a binary format as much as, well, I mean, it's a binary format, but it's not a good compiler target. Like, there's no point in compiling C to JVM to the JVM basically, right? Well, it needs wide browser support. Well, I mean, it's cool that you can run in the browser, and that's what most people care about. But I mean, guess everyone is using V8 now. Well, the SpiderMonkey, or like whatever the Mozilla's web engine is called now, is totally happy to run Wasm as well, right? So they've got a pretty good Wasm engine as well, and they're also working on more Wasm engines, right? Like Wasm Time, which is their standalone WasmJIT, which does not need to run inside a browser, and that's based on CraneLift, which is their new code generator compiler backend that I eventually intend to use for quick Rust builds as well. So there's some very exciting stuff going on there. And I think WebAssembly is, well, I'd hope that WebAssembly really is going to be big and well supported in the future, because I think it would be a good step forward for our industry. But we'll see how things turn out. It's really hard to predict these things. Anyway, so what we have is a bit of PureScript code, which really just wraps up a bunch of JavaScript that writes the magic invocation into a buffer, writes that buffer to a file, and then interprets the file it has just written as a WebAssembly module using Node's built-in WebAssembly engine. And I think that's a pretty good point to say we're just going to stop for now, and then I'll try to be a bit more regular in my streaming, and maybe tomorrow we can write a bit of an abstraction over this thing so that we don't have to keep track of the offsets ourselves by hand, and we'll try to write a module that actually contains some logic and not just magic header file, like header of bytes, right? So thanks everyone for hanging out. I'm happy that this is working out so well, because if this keeps going, I think there's going to be lots of fun. Cheers, everyone.